Okay, so we just talked about how we set up or justify the formula for what we call the disk method, a method for finding volumes of solids of revolution. In particular, we looked at a horizontal axis, the x-axis. So what I'd like to do is kind of do another example that might be a little bit more involved than the first one. So let's consider a region bound by several curves. So it's going to be bound by y equals the square root of x, the line y equals 4, and the line x equals 20. And what we're now going to do is we're going to rotate that area around the line y equals 4. All right, so in these cases where we're asked to find volume of solids, I would highly encourage you all to begin by sketching a graph. So let's do that first. Let's go ahead and we're going to get a sketch and draw a cross section on that sketch. So let's go ahead and do that first. So off to the side here, let's consider what we're working here. Now this is all, I'm going to warn you, this is not going to be to scale, but that's just so it's reasonable to see. So here's the y-axis, here's the x-axis. Now our first curve that we're dealing with is the square root of x. Now square root of x, you guys aren't allowed to use graphing calculators, so this is definitely a curve you should be familiar with in terms of how to draw it. And a radical like the square root of x begins at the origin and it's increasing at a decreasing rate. So this is going to be a rough sketch of y equals the square root of x. We're also told it's bound by the line y equals 4. So that means that we're going to need to move up the x-axis, the y-axis, excuse me, to 4. And let's draw a little horizontal line here that sort of defines that space. So this would be the line y equals 4. And then we are also bound by the line x equals 20. So that means we have to go out the x-axis to 20, and then we are going to draw a boundary line there. So that would be that line right there. Kind of missed the mark, but you guys probably get the idea. Yeah. All right. Try not to be a perfectionist. So this is the line x equals 20. All right, so at this point we can kind of see what the area is that we're dealing with here. So I'm just going to go ahead. I'm going to shade this in just so it's clear that we are going to take this bounded region and rotate it. Now in this particular case, we were asked to rotate it about the line y equals 4. So I'm going to go on to y equals 4, and I'm going to draw another one of those little swirly doos to tell us this is where it's going to be rotated. Right, and then at this point I'm also going to draw our cross section. So we've got our area. Now the cross section can be a really important tool in terms of the later steps in this problem. So what we want to do is we want to consider if we were anywhere along the axis that we're rotating nearby, so anywhere along this horizontal line, some point. I'm just going to pick a point in between and call this x. What would a cross section that gets rotated look like here? Well, we would start on our axis of rotation, and it's going to go up to the boundary curve. So this little sliver of area right here is representative of one piece of this region that is going to get rotated. So this is what we refer to as one of our cross sections. All right, so we're just going to kind of leave that there for now, and we'll come back to this later. All right, so we've got our sketch. Now, the second thing that we are going to need is we are going to want to get our bounds. Specifically, what are the bounds of this region? Now we notice that it clearly ends at 20, but what about where it begins? Well, it begins at this intersection right here. So what we now need to do is figure out what is that x value. And the way that we do this is we're basically looking to see where these two curves, namely y equals the square root of x and y equals 4, intersect. So this is just sort of a nice little algebra problem that we can do here. So this is going to be the intersection of y equals the square root of x and y equals 4, the two curves. So we just take those two, we set them equal to each other. We're trying to figure out what is the x value where these two curves are equal. And if we were to square both sides here, we would see that x is equal to 16. So we now know that it's no longer unknown. This point right here is x equals 16. All right, so let's go ahead and make a note of our bounds here. So we're going to go from x equals 16 to x equals 20. I'm going to put a little bubble around there because this is one of the two crucial pieces of information we're going to need to set up our integral. All right, and then the third thing that we need now is we need a formula for the radius of a disk, namely big R of x. Now remember, these disks are generated from every single one of these cross sections, one of which we drew here, being rotated around the axis of rotation. So this is why we drew this cross section, is this is going to be very telling to determine what our radius is. So this, the height of this cross section right here is going to be r of x. So what is that height? Well, if you can't see it right away, we could think about it this way. The height for any of these cross sections that we would draw would be, I'm going to kind of get close here. So the distance from the curve to the x-axis, this we know is just the square root of x. But we then want to remove this from that quantity, and this distance is just 4. And what remains is the cross section that we're actually after. So what we can now do is we can say that that actual cross section is the square root of x minus 4. So sometimes we have to do this, especially if we're moving our axis of rotation around. All right, so now we can go back here, we can make note of this piece of information, that our axis of rotation, or excuse me, our radius is going to be the square root of x minus 4. So once we've got these bits of information, now we should be able to go ahead and set up our volume formula. So we'll go ahead and we'll do this. So to get our volume, we're going to use the formula for the disk method that we laid out above here. So it's going to be v is equal to the integral, in this case from 16 to 20, pi times, now in this case our radius is the square root of x minus 4, which we then square, and we're going to integrate that with respect to x. All right, now in some cases you might just be asked to set up an integral. There it is. The integral for volume has been set up. If we need to evaluate this, now we're going to need to get it into a form that we can actually integrate. So a couple things that we're going to do, like before, I'm going to pull that pi out front. So pi from 16 to 20. And then I'm also going to square out this square root of x minus 4. Now, I know you guys are in calculus now, but sometimes it's still tempting to want to distribute exponents when it's not appropriate. So remember, what we're doing here is we're essentially multiplying square root of x minus 4 times square root of x minus 4, foiling if you're used to using that term. So if we multiplied all this out, we would have x minus 8 times the square root of x plus 16 integrated with respect to x dx. Now we integrate. It's probably going to be helpful to think about this as negative 8 times x to the power of 1/2 when it comes to integrating. And let's move on to that next step. So if we integrate, we're going to have pi times this antiderivative, which is going to be 1/2 times x squared, so that's the antiderivative of x, minus 8 times, so if we add 1 and divide to 1/2, we're going to get 2/3 x to the power of 3/2, and then plus 16x. So all we did there is we took the antiderivative, and now we're going to evaluate that from 16 to 20. This one doesn't work out particularly nicely. You're probably going to need your calculator for this, but in the end, I'll let you check that calculation, but we end up with this something that's approximately 0.96 cubic units. And that would be an approximation of our answer. All right, so a slightly more difficult one. There's a lot of front-end work where we had to set up this, but the method of the disk method, the methodology, the mechanics, it's all still there. It's finding the bounds, it's then getting that radius, setting it up in the formula for the disk method, and then evaluating.